So hello Year 12, and hello for the last time for a few weeks, because after this I will be handing over to Dr. Butterworth, who will be continuing with topic 13A, Born Harbour cycles. So it's the last video for me for a while, which many of you will be happy with. So we're going to finish off our topic of entropy today, and there's less new material than you might think. So we're just going to be looking at free energy graphs and kinetic control. Here's the spec, and this is what we're going to focus on today. We're going to continue to use delta G to determine whether or not a reaction is feasible, and if it is or is not, determining the temperature at which a reaction is feasible. We're then going to have a look to understand why a reaction for which the delta G value is negative may not occur in practice, and know that reactions that are thermodynamically feasible may be inhibited by kinetic factors. So that's this. Some processes that should be and are spontaneous don't occur in reality. Why not? You may be wondering about spec point 20. Well, we're going to come back and have a look at that once you've completed the topic equilibrium 2, because you need to be able to calculate equilibrium values in order to use this successfully, and it'll be covered in equilibrium 2 and in 5th lesson, tying all of this stuff together. There is some information at the end of this PowerPoint for anyone who wants to get ahead of the curve, but that is by no means essential viewing, and there will be no questions on it. A reminder, Gibbs free energy delta G here is just another way really of calculating the entropy change of the universe, because delta G is just minus del T delta S total. And remember, we said that for a spontaneous process the entropy change of the universe must be greater than 0. In other words, that must be positive, so therefore delta G must be negative. So delta G must be less than 0 for a spontaneous process, and you just need to learn that. There's no shortcut. You just need to learn that delta S total needs to be greater than 0, delta G needs to be less than 0. And here is an example. Calculate the free energy change for the reaction at 400K and 600K. So delta G equals delta H minus T delta S. The enthalpy change plus 62 kilojoules per mole. Let's do this at 400 Kelvin, 400 times plus 132.8, but that's in joules. We need to put it in kilojoules. So we do that equals plus 8.88 kilojoules per mole. In other words, that's not spontaneous. In contrast, at 600 Kelvin, plus 62 minus 600 times by 132.8 over 1000 equals minus 17.7 kilojoules per mole. So that is spontaneous. And what's the minimum temperature? Well, from this we know that delta G equals 0 equals delta H minus T delta S. So therefore the temperature is delta H over delta S. We must put them in the same units. So let's just make it 62,000 divided by 132.8, and that gives us an answer of 467 Kelvin. Okay, so hopefully that's fairly straightforward. Okay, before we move on, you just need to recap the equation of a straight line. A straight line, as you will hopefully remember from GCSE, can be written in the format y equals mx plus c, where m is the gradient and c is the y-intercept. So here it's crossing the y-axis at 2, so we know that C is 2. And if we look at the gradient here, it is going up 2 in 1, 2, 3, 4, 5, 6, 2 over 6. So therefore this equation for this, y equals a third x plus 2. And we can do the same thing with a negative gradient. So if we've got a slope like this, then here the intercept is clearly 5, so C is 5. The gradient, well, now we are going down 2 in 1, so the gradient is minus 2, okay? Do be careful of that, and that's going to be really important. So if you want to have a go, here's 3 for you to have a go at, and I will put the equations underneath these graphs after the break. There you go. Now, why do we care? Why do we want to know this? Well, if we take that equation y equals mx plus c, we can imagine plotting delta G on the y-axis against temperature on the x-axis. And if we do that, we can see delta G equals delta H minus T delta S. So if we plot this, we can see that the intercept on the y-axis is going to be delta H. We can read that off the graph where it crosses the y-axis. So y-axis intercept. The gradient is minus delta S. So if you plot a graph of delta G on the y-axis against T on the x-axis, the gradient will be minus delta S and the y-intercept will be delta H. So this is a way that we can actually plot data to determine the values of delta H and delta S. If the graph looks like this, and we've got various values of delta G against temperature, we can extrapolate back to 0 Kelvin, T equals 0. Remember, this must be in Kelvin. T is 0 to find a value for delta H. So that value, where T is 0, gives us delta H. The gradient here is clearly negative. So let's say it's minus 10. Then minus 10 equals minus delta S. Therefore, delta S is plus 10. I'm not giving you units, but the point being here is this had a negative slope, so it means that delta S is positive. As I've said up here, delta S must be positive, otherwise the gradient would be a minus minus, in other words, a positive slope. Because delta S is positive, minus delta S is negative, and that's why we've got this negative slope. Okay, so if the entropy increases, delta G gets less positive, more negative as the temperature goes up. In contrast, if you plot your points and the gradient is increasing, so that we've got a positive slope, now that means that, for example, plus 10 is minus delta S, so delta S is minus 10, okay? And it's because of this minus here, because M, the gradient, is minus delta S. So delta S must be negative, so the gradient is, delta S must be negative, so the gradient is a minus minus, i.e. a positive slope. So don't forget that the slope measures minus delta S, which means that delta S must be negative so that you get a minus minus, in other words, a positive slope. And again, extrapolate back here to T equals 0 to find a value for delta H. Here's an example. When lead 2 nitrate is heated, it decomposes according to the equation. Plot the following values of delta G against T and use the graph to find delta H reaction and delta S system. At what temperature does the reaction become feasible? Now, I decided not to stick a video of me doing this, but you can trust me when I say this took me, including the time to open Excel, 3 minutes to do that. I've got temperature against delta G, I typed in the numbers, I created a chart, and that's this, and then I added a trend line to this. Look, I haven't labelled the axes, but this here, this is temperature in Kelvin, this is free energy, or delta G in kilojoules per mole, and I fitted the equation. I got y equals mx plus c immediately. All right, 3 minutes, that's what it took me. So for you guys, even going at a snail's pace, it shouldn't take you much more than 5 minutes to do the same thing. Right, the intercept, we're told here, c, which is 602, and that equals delta h. So therefore, delta H equals plus 602 kilojoules per mole. In other words, this is endothermic. What about this? Well, this is M. So M, our gradient, equals minus 0.8767, and that equals minus delta S. So delta S equals positive 0.8767. But remember, this is in kilojoules per mole on the gradient here. So we need to times that by 1,000 if we're going to put it in joules per Kelvin per mole. So delta S equals 877 plus 877 joules per Kelvin per mole. Okay. The final question here is, at what temperature does the reaction become feasible? Well, T equals delta H over delta S, which equals plus 602,000. Remember, we must have it in the same units, over delta S, which was plus 877, and that gives an answer of 686 Kelvin. Of course, it's plus 686 Kelvin, and that kind of makes sense because we know it's going to be between 600 and 900. Going back to the graph, we can see that delta G is 0 here, and that is pretty much at 700 Kelvin. So we can have faith in this value, 686 Kelvin. It ties in with our graph. The other thing we've just got to look at quickly to finish off is the difference between thermodynamic stability and kinetic stability. Now, what I've plotted here are called free energy diagrams. They're very similar to the diagrams that you're used to. The difference is we are plotting Gibbs free energy here, G, instead of H. So we're plotting free energy instead of H, but the idea is still the same. We can see here, if the reactants are higher in free energy than the products, then delta G, the change in free energy, is negative. This means free energy is released, not enthalpy, not quite the same, but free energy is released. In other words, the reaction is spontaneous. So if the products have less free energy than reactants, i.e. if delta G is negative, the reaction is spontaneous. Over here, however, we have a situation where the products are higher in free energy G than reactants. In other words, delta G is positive. delta G is greater than 0. And such a reaction is not spontaneous. We would say a reaction like this is thermodynamically unstable because the reactants will and want to form products. Our reactants are not stable. They're not going to sit around there. They will eventually react to form products because there's an increase in entropy of the universe, a decrease in free energy. In contrast, for a reaction like the one on the right, this is thermodynamically stable. Our reactants will sit around there doing nothing. They are stable. They're not going to turn into products. They will never, ever react to form products because it is unfavourable, because there's a decrease in the entropy of the universe. There's an increase in free energy there. So a spontaneous reaction is unstable, but a reaction that is not spontaneous is stable. This won't fall apart, this will fall apart. But there's another type of stability. And both of these are reactions that are spontaneous, where the reactants will naturally form products because delta G is negative. But this first reaction here, the green one, has a low energy barrier, and therefore it is a fast reaction. The purple has a very high energy barrier and so a very slow reaction. We would say that this purple one is kinetically stable. Even though the reactants want to form products, they can't do so without a lot of energy being put in. The green one, however, is kinetically unstable because it is easy for those reactants to form products. So it is possible, as the purple one shows, for a reaction to be thermodynamically unstable. In other words, it wants to fall apart into products, but it can't do so because of the high energy barrier. And this is one example of kinetic stability. If we look at graphite versus diamond, so for the reaction diamonds turning into graphites, delta H is products, so that's graphite 0 minus reactants 1.897, so therefore it is minus 1.897 kilojoules per mole. Diamond turning into graphite is, in other words, exothermic. In terms of entropy, delta S, products, graphite 5.740 minus 2.38, which equals 3.36 joules per Kelvin per mole. Delta G equals delta H minus T delta S, which equals minus 1.897 minus, well, let's take room temperature, 298 Kelvin, times by 3.36 divided by 1,000, and that equals minus 2.90 kilojoules per mole. In other words, diamonds are thermodynamically unstable. So diamonds want to fall apart into graphite, and they will do over millions of years. Why don't they? Well, because there's an absolutely massive barrier between reactants and products, so they are kinetically stable. So all those diamonds that you're wearing, earrings, nose rings, wherever else you might have them, they are slowly converting back into graphite, but it's very slow. It is spontaneous, but there's a huge free energy barrier to do that. Right, so for the majority of you, this is where you'll want to switch off. What you need to do for lesson 4, there is another quiz on Google Classroom. It is mostly self-marking, and for those questions, the numerical questions, remember to pay attention to the required format, usually to 3 significant figures, although not always, correctly rounded, no units, take care with your kilojoules versus joules. Some questions, because I have given you some exam questions, some questions are longer answer. I'm going to put in the effort to mark all of your answers according to the mark scheme, so the least you can do is put some effort into your replies. It may take you 2 minutes to do it. It's going to take me a lot longer than that to go through all those answers. And 2 questions at least require you to plot a graph. There's no excuse not to do this. If you don't have graph paper, then either use Excel, or if you don't have Excel, Google Sheets. It took me 5 minutes to plot this on Google Sheets, and that included the time it took me to research how to add a trend line to a graph in Google Sheets. So there's really no excuse. I don't want any of you leaving the answers blank because you couldn't plot a graph. Okay, good luck. Hope it goes well. Enjoy 13A. Okay. If you're still with me, then I'm assuming that you are either a perfectionist and cannot bear to leave that 1 spec point undone, or that you're really enjoying this topic and want to see where it's going. So this is going to be very hard. This is not for those people who are worried about maths. It's not going to be easy, but it is where the topic is going. And it also is so powerful, and I'll hopefully show you why. So we're looking at equilibria and how that relates to free energy. But I should stress, this is not examinable until you've done the equilibrium 2 topic. And even then, these are probably the hardest questions that could ever be thrown at you. So, this expression here is extremely important. Delta G, the free energy change, equals minus R, which you've used before in PV equals nRT. It's the ideal gas constant. T is obviously the temperature in Kelvin. Log, natural log, so the natural logarithm. And if you're wondering what on earth is that, probably you don't want to go any further. And K, which is the equilibrium constant. And that is the really important expression. So, first, let's assume a reaction has formed 99% products at room temperature. Well, we know that the equilibrium constant K is the concentration of products over the concentration of reactants. So, under this condition, the equilibrium constant K is 99% over 1%, or 99 moles over 1 mole, which is 99. So let's assume room temperature. Delta G is minus R times room temperature in Kelvin times the natural log of 99. And if you work that out in your calculator, you'll find that the free energy change is minus 11.4 joules per Kelvin per mole. It's negative, indicating that this reaction is spontaneous. So, let's assume that a reaction has formed exactly 50% products. Again, our equilibrium constant K would be something like 50 millimoles divided by 50 millimoles, or 50 moles divided by 50 moles. Concentration, so moles per dm cubed, which equals 1. Delta G is minus R times the temperature, again let's assume room temp, times log of 1. Now hopefully you guys know that the natural log of 1 is 0, so the whole expression is 0. And here we have a reaction that is on the verge of being spontaneous, of spontaneity. let's imagine the opposite. Let's assume that the reaction has formed just 1% products at room temperature. So the equilibrium constant, concentration of P over R, so that might be, for example, 1 millimolar divided by 99 millimolar, which will give us an equilibrium constant K of 0.01. Delta G is minus RT log 0.01, which comes out at plus 11.4 kilojoules per mole. In other words, it's not spontaneous. And we can begin to work out how the value of K and the value of G are related. So if you work backwards and assume that delta G reaction is plus 30 kilojoules per mole, then you'll work out that the amount of products compared to reactants is way, way, way less than 1. Very little product. In other words, there's no reaction. If delta G is positive, but only slightly positive, then there is a partial reaction. We get some products, but the amount of products compared to reactants is less than 1. So we get some product. In other words, we get an equilibrium mixture. If delta G is exactly 0, there are some reactions where it's almost exactly 0. The amount of products and reactants is virtually equal to 1, a 50-50 mix of each. And so this is a real equilibrium mix. And think about the Haber process. And if you want, go back to your GCSE and find out exactly where you got a 50-50 mix of products and reactants, 50% yield, and you will find out where delta G was 0. If delta G is slightly negative, we get an equilibrium mixture again, but here we get more products than reactants. And if delta G is very negative, so less than minus 30 kilojoules per mole, we get a complete reaction. Essentially, there's almost no reactants. And we would say that the reaction has gone to completion. And for any value of delta G, you can work out backwards what the equilibrium constant is. So I'm just going to show you two reactions here. For the reaction, carbon monoxide and water going to carbon dioxide and hydrogen, it's a reversible reaction. The equilibrium constant is 1.038 times 10 to the 5 at 298 Kelvin and 1.094 times 10 to the 4 at 350 Kelvin. Calculate the value for delta G at each temperature. Okay, so at 298, delta G equals minus R, 8.314, times T, 298, times by the natural logarithm of the equilibrium constant, 1.038 times 10 to the 5. And that equals minus 28.6 kilojoules per mole. So about minus 30 kilojoules per mole. So it's almost entirely gone to products. And yeah, we can tell that, can't we? The equilibrium constant is about 10,000. Very high. There's only 1 in 10,000 bits are still reactant. At 350 Kelvin, delta G equals minus R, minus 8.314, times T, 350, times by the natural logarithm of 1.094 times 10 to the 4. Okay, so we've got about tenfold less product here. So let's see how that affects things. So that is minus 27.1 kilojoules per mole. In other words, less products. And we can relate this to so many ideas we've already seen. Le Chatelier, we're raising a temperature, we're getting less product, so that is already suggesting to us that the reaction must be exothermic, going to the right hand side. Construct simultaneous equations where delta H and delta S are the two unknowns. Solve these equations to find the entropy change and enthalpy change of the reaction. So the two equations are minus 28.6, that's delta G, equals delta H, which we don't know, minus T, 298 delta S. And the other equation is delta G minus 27.1 equals delta H minus T 350 delta S. Okay, so the easiest thing to do is equate them both to delta H. So delta H equals minus 28.6 plus 298 delta S, and that comes from the first equation, but it also equals minus 27.1 plus 350 delta S. So now we can group these onto the same sides. So therefore 350 minus 298 delta S. So on that side we would have 52 delta S, and on the other side we'd have minus 28.6 plus 27.1, which equals minus 1.5. Remember, of course, that is in kilojoules per mole. And therefore we can say that delta S equals minus 1.5 divided by 52, which equals about 29, minus 29 joules per Kelvin per mole. And we've worked out what delta S is, so we can then substitute that idea back into the equation to work out what's going on here. So let's substitute it into the negative, the second one. So delta H equals minus 27.1 plus 350 delta S. And of course, remembering that that is going to be in kilojoules per mole per Kelvin. So that equals minus 17.0 kilojoules per mole. Okay. So we can work out delta H, and it is exothermic as we expected. And this is why the equilibrium goes down as the temperature goes up, just like Le Chatelier says. Another thing to flag up is actually this is a very small decrease in entropy. And if we were to look at that equation there, 2 gas molecules on the left versus 2 gas molecules on the right, we wouldn't really have a feeling for the sign of delta S system. We might expect it is about 0, and that small value of delta S supports that. Second example here, and this really does tie in with what you would learn in equilibrium 2. At 200 degrees C, 2.4 moles of carbon monoxide and 2.4 moles of steam were left to reach equilibrium. At equilibrium, 1.6 moles of both hydrogen and carbon dioxide were present. Determine the value of the equilibrium constant Kc at this temperature. Okay, so at the start, we've got 2.4 moles of that, 2.4 moles of that, and we've got none of that and none of that. At equilibrium, we've got 1.6 moles of CO2 and 1.6 moles of hydrogen. Well, one of those forms one of those, so if there's 1.6 of those, there can only be 0.8 of those, and there can only be 0.8 of those. Now you might be worrying here that we don't know the volume. So we can't work out a concentration or a pressure, but actually it doesn't matter, because the equilibrium constant there is the concentration of CO2 times by the concentration of H2 over concentration of CO times the concentration of H2O. And that equals the number of moles of CO2 over volume times by the number of moles of H2 over volume divided by the number of moles of CO over the volume times by the number of moles of H2O over the volume, okay? Because concentration is moles over volume. But these volumes cancel. So it is just the number of moles of CO2 times the number of moles of H2 over the number of moles of CO times the number of moles of H2O. This only works when you've got the same number of gas molecules on both sides of the equation. It doesn't work for every equation, but this here is why we're not told about the volume. So that equals 1.6 squared over 0.8 squared, and that gives a value of 4. And I should have been able to work that out. Okay. Calculate the free energy change of the forward reaction at this temperature. So delta G equals minus RT log K, which equals minus 8.314 times by the temperature at 200 degrees C, so that's 473 Kelvin, times by the natural log of 4, and that equals minus 5.45 kilojoules per mole. Okay, it's not very negative at all, and that's why we've got quite a mix of products and reactants, because it's only slightly negative, but we have got more products because it's a negative number. Given that the enthalpy change is minus 42 kilojoules per mole, calculate the entropy change of the reaction. Well, we know that delta G equals delta H minus T delta S, so delta S equals delta H minus delta G over T. Let me just check that. Delta H minus delta G over minus T, actually. And that equals minus 42,000 minus 5,450, all divided by minus 473. Lots of options for problems here. So plus 77 joules per Kelvin per mole. So now that I've corrected that problem, I can keep going with the rest of the question. D. Calculate the new equilibrium constant and the new amounts of each chemical at 300 degrees C. Well, we now know that delta S is minus 77 joules per Kelvin per mole. So at 300 degrees C, which is 573 Kelvin, delta G equals delta H minus T delta S, assuming of course that they don't change, which they will do, but only slightly. So minus 42 minus temperature, 573, times by delta S, minus 77. But of course we need to make sure that everything's in the right units for that. And that gives us an answer of plus 2.3 kilojoules per mole. In other words, we might have said a couple of lessons ago that that was no longer spontaneous. But actually what we now know is that this is an equilibrium where reactants predominate. So it's only slightly positive, so we're going to have an equilibrium mixture. Okay, calculate the new equilibrium constant. If delta G equals minus RT natural log of K, we can rearrange that to say that natural log of K is minus delta G over RT, and therefore K equals E to the minus delta G over RT, which equals exponential of minus 2, let's put this all in joules, minus 2,300 or so, divided by R, 573, times by, R times T. like that. Okay, if we work that out, we get an answer of about 0.62. But finally, we're asked for the new amounts of each chemical. So we've got to turn that back into an amount. Now there are some very hard versions of this question, but this one's not too bad. So we know that initially that's 2.4 and that's 2.4. Well, let's say that the end amount of carbon dioxide is X. Well, the end amount of hydrogen must be X as well, because you make 1 mole of each. The amount of carbon dioxide must be 2.4 minus X, and the amount of water must be 2.4 minus X, because each of those have lost one of those, makes one of those, one of those makes one of those. So our equilibrium constant K, which equals 0.62, equals the concentration of CO2, or the number of moles of CO2, times by the number of moles of H2, over the number of moles of CO times the number of moles of H2O. Remember, it would be concentrations, but we've seen that that's not essential here. So that equals X squared over 2.4 minus X squared. And you might be thinking this is going to involve a quadratic, but it doesn't, because we can square root both sides to get the equation square root of 0.62 equals X over 2.4 minus X. So therefore X equals 0.79 times 2.4 minus X. In other words, 1.79x equals 1.89, so therefore X equals 1.89 divided by 1.79, which is 1.06. In other words, we have 1.06 moles of this, 1.06 moles of this, 2.4 minus that, which is 1.36 and 1.36. And we can do a check that that works. If we do 1.06 squared divided by 1.36 squared, we get 0.6-ish. So that's close enough given the approximations that we've made. So we can now see we have slightly more reactants than products. Okay, just to reassure you, these are about the hardest questions you could ever get at A-level. In fact, both of these have been taken from a first year undergraduate textbook, so don't freak out. But what I wanted to show you was exactly how powerful these equations are when you really get to use them. So from a little bit of information here, we've managed to work out firstly the delta G, and then we've managed to work out the entropy change of the system, and then we've worked back at a new temperature to work out the new equilibrium concentrations of each species. And all of these just done using those two equations, delta G equals minus RT natural log of K, and delta G equals delta H minus T delta S. And later on we'll even go on to link delta G to voltages, and we'll see just how powerful free energy really is. Thank you for watching.